Maharshi Karve Sri Shikshan Sanstha's Cummins College of Engineering for Women, Nagpur. I am Dr. Sanjeevani Shastri from Department of Physics. Today we will see Part 3 Electrostatics, that is capacitors. Let us see what is a capacitor. A combination of two conductors placed close to each other is called a capacitor. One conductor is given a positive charge and another is given a negative charge. See the figure for symbol of a capacitor. The charge on the positive plate is called as the charge on the capacitor, and the potential difference between the plates is called the potential of a capacitor. We get Q is equal to C into V, where C is called as capacitance of the capacitor. The capacitance depends on the shape, size and geometrical placing of the conductors and the medium between them. The SI unit of capacitance is coulomb per volt or farad. There are various types of capacitors. First, consider parallel plate capacitor. It consists of two large plain plates placed parallel to each other with a small separation between them as shown in figure. If A is the area of each face and D is the distance, assume that the space between the plates contain vacuum. Thus we get C is equal to epsilon 0 A upon D. Another type of capacitor is spherical capacitor. It consists of a solid or hollow spherical conductor surrounded by another concentric hollow spherical conductor. Inner sphere has a radius R1 and outer has radius R2. Inner sphere has given a charge of positive Q and outer as negative Q. The capacitance will be given by C is equal to 4 pi epsilon 0 R1 R2 upon R2 minus R1. The next type of capacitor is a cylindrical capacitor. It consists of a solid or a hollow cylindrical conductor surrounded by another coaxial hollow cylindrical conductor. Let L be the length of the cylinders and R1 and R2 be the radii of inner and outer cylinders. Suppose positive Q charge is given to the inner cylinder and negative Q charge is given to outer cylinder. The capacitance is given by C is equal to 2 pi epsilon 0 L upon natural log R2 upon R1. There are two methods in which we can combine the capacitors. First one is series combination. If a negative plate of one capacitor is connected to the positive plate of the other and so on, thus the combination is called as a series combination. In figure we can see that there are three capacitors C1, C2 and C3 connected in series. If the combination is replaced by a single capacitor of capacitance C, it will store the same amount of charge for a given potential difference as the combination does. Thus we get 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 and so on as the equivalent capacitor. Another method of combination is parallel combination. If all the positive plates are connected together and all the negative plates of the capacitor are connected together, then the combination is called as parallel combination, as shown in figure. The potential difference on each capacitor is the same in parallel combination, but the charges may be different. The equivalent capacitance of the combination is given by C is equal to C1 plus C2 plus C3 and so on. force between the plates of a capacitor. The plates of a parallel plate capacitor attract each other because one plate is kept at positive potential and another is kept at negative potential, and the force of attraction is given by F is equal to Q square upon 2A into epsilon 0. Capacitor can store energy. Energy stored in a capacitor is in electric field is given by U is equal to half QV or U is equal to half CV square. Another important property of a capacitor is dielectric. In dielectric material, effectively there are no free electrons. In such a material is placed in an electric field, the individual dipoles experiences torque due to electric field. This is the case for polar material. In non-polar material, if they are placed in electric field, electron charge distribution is slightly shifted opposite to the electric field. Thus, if a dielectric material is placed in an electric field, dipole moment appears in any volume and we say that it gets polarized as shown in the figure. Consider a parallel plate capacitor with dielectric. Due to the presence of dielectric, the capacitance of a capacitor is increased by a factor of K. When the space between the plates is filled with a dielectric of constant K. Thus we get C is equal to K epsilon 0 A upon D, where K is dielectric constant. Energy in the electric field in a dielectric. Consider a parallel plate capacitor filled with dielectric constant K. The energy stored is U is equal to half CV square, which we have already seen. The energy density is given by U is equal to half K into epsilon 0 E square, where capital E is nothing but V by D is the electric field between the plates. That is all for capacitors. Thank you. Visit our website www.cummins.college.edu.in or drop me a mail on sanjeevani.shastri@cummins.college.edu.in or contact me on 98503 85463 for any queries. Thank you.